Existing video language embeddings match clips with its text description. We propose to use hierarchical long-term videos with its summary text to capture both what is happening and why is it happening. The availability of summary annotations in recent datasets and our novel hierarchical setup enables this embedding learning. Summary are descriptive text telling the high-level intent, whereas narrations are text sentences describing the current action. Our proposed pre-training improves both long-term and short-term representations, as seen in its downstream task performance in both zero-shot and fine-tuned settings on Ego 4D, Sherrod's Ego, How to 100 Million, and Epic Kitchens. The visualizations also show the desired hierarchy between long-term and short-term features. Overall, our work goes beyond capturing what the person is doing now by additionally capturing what the person aims to do. Conventional video language embedding only matches short-term clips with their corresponding narrations, thus capturing what is happening. Our hierarchical video language embedding learns both short-term and long-term relations, thus capturing what is happening and why is it happening, a crucial step towards better activity understanding. Note that here summary text in blue box represents the high-level intent of the activity, whereas narrations in green box represent instantaneous action. To our knowledge, ours is the first work to create a hierarchical video language embedding between seconds-long narrations and minutes-long activities. The key idea is to use both short-term narrations and long-term summaries to embed into a common embedding space for improving video language representations. Our model design addresses constituent technical challenges. We circumvent typical expense of long-term feature learning by using aggregation of short-term features. We show how jointly training with two levels of annotation staves off catastrophic forgetting of either layer. Our HierVL achieves state-of-the-art performance on Ego 4D long-term anticipation, Sherrod's Ego action recognition, and Epic Kitchens 100 multi-instance retrieval, both zero-shot and fine-tune. For pre-training, we use Ego 4D, a dataset having 3,670 hours of video with 3.8 million narration and 120,000 summaries. Narrations capture short-term actions like picking up tennis ball from ground. Summaries capture long-term intent like playing tennis in a court. These hierarchy in annotations make Ego 4D suitable for our pre-training. An example is shown on the right. The training architecture is as follows. For child-level contrastive learning setup, clips within a batch are sampled from different videos. Visual and text samples are passed through a visual and text encoder respectively to obtain features. The corresponding features are positives for the contrastive learning, similar to previous works. For the parent-level contrastive learning setup, we take video clips, narration, and the overall summary text. We obtain short-term features using short-term visual and text encoder used previously. Finally, we aggregate short-term features into a long-term feature and match it with the summary feature. Here is what the overall architecture looks like. We employ joint training. We first train the child-level setup for M batches and then parent-level training for one batch. And we continue the process. Here is the visualization of the learned embedding. This is a T-SNE plot comparing the learned text representation for parent level and child level features. We see that HierVL captures a natural hierarchy between parent level and child level features, whereas EgoVLP does not. First, we evaluate the general quality of learned video features. The first task is Ego MCQ, which is originally proposed in EgoVLP. The task here is to choose the correct video clip for the given narration. To evaluate the long-term understanding of videos, we additionally propose summary MCQ. Here, the model needs to choose the correct long video for the given summary text. This task is important to capture minute-level understanding of videos as compared to traditional second-level Ego MCQ. Further, we have Shuffle MCQ, where the model needs to choose the correct order of clips in a long video. This task evaluates if the model is capturing the temporal nature of videos as opposed to simply averaging the features. Here are the pre-training results. We perform better than the baseline and ablations in both Summary MCQ and Shuffle MCQ tasks. All the methods have similar performance in short-term Ego MCQ. Now we show the performance of our method on several downstream tasks. The first downstream task that we focus on is Ego 4D long-term anticipation. This task takes as input a video clip up to a certain time and predicts next 20 actions. Our model can reasonably anticipate next action in challenging in the wild videos. Here are the results. Our method performs better than all the published work on verb edit distance, noun edit distance, as well as action edit distance. Our method also tops the public leaderboard at the time of submission. The next downstream task is Shared Ego action recognition, where the task is to classify a given video segment into one of the possible 147 classes. Our method achieves state-of-the-art performance in both zero-shot and fine-tuned settings. The next downstream task is Epic Kitchen's multi-instance retrieval. For a given video, the task is to retrieve narrations such that they are semantically similar. And for a given narration, the task is to retrieve videos that are semantically similar. Over here as well, our method achieves state-of-the-art performance in both zero-shot and fine-tune settings. The last downstream task is How to 100 million long video classification. The model in long video classification task needs to choose the correct category of a long video. Finally, in this task as well, our proposed method outperforms the baseline. To conclude, we propose a novel hierarchical video language embedding. In addition to current embeddings focusing on what the person is doing now, we also focus on what the person aims to do. This hierarchical video language embedding improves both short-term as well as long-term representations. Our model achieves state-of-the-art performance on a variety of short-term and long-term video tasks.